Hi team, today we are going to be talking about 10.4, mechanical waves. Specifically, we are going to be discussing sound and an important property of sound called resonance. Right now, I want you to imagine a world where you can't hear. So imagine that you're deaf. Imagine that you can't hear my voice right now. Imagine that when you're watching Star Wars, you can't hear the sound effects of lightsabers or the dramatic music giving it its mood. That world would exist if we didn't have mechanical waves. Today, we're going to talk about how sound is created. We're going to talk about how our ears are able to hear, and we're also going to talk a lot about how musical instruments actually create sound waves. Our objectives for today: we're going to review differentiation between electromagnetic and mechanical waves. We'll identify the properties of sound waves. We'll describe the properties of standing waves, which is an important thing for instruments. We'll define harmonics, and we'll do some calculations with that, as well as defining resonance and using harmonics and frequencies to perform more calculations. So first, let's review electromagnetic versus mechanical waves. These are the properties that you saw on the last video that are most important for differentiating between electromagnetic and mechanical waves. But specifically, remember, electromagnetic is light. It is packets of energy. They are emitted from a source like the sun or a fire or an atomic bomb, and they can travel in a vacuum or empty space. Mechanical waves, which we're going to talk about today, have to be caused by some sort of force, and they have to travel through some medium or material. Specifically, a guitar string has to be plucked, that's the force, to vibrate as a mechanical wave. Mechanical waves can be either transverse, like a guitar string, or they can be longitudinal, like a sound wave. But they also travel a lot slower than electromagnetic waves, which is why our ears, for example, can hear but can't see. The two specific examples of mechanical waves we'll talk about today are guitar strings, which vibrate as transverse waves, and we're also going to talk about actual sound waves in air, which are longitudinal waves of air pressure. So first, what is sound? Well, we know sound is a mechanical wave. It's a longitudinal wave, and it's a longitudinal wave caused by air pulsating back and forth at different pressures. This is what we actually perceive. Our ears pick up the change in pressure, and we perceive that as a wave. Pitch is kind of the note that you hear, whether it's a do, like a low sound, or a do, really high sound. That's frequency. Lower frequencies correspond to lower notes. Higher frequencies correspond to higher notes. The volume, whether it's really, really quiet, is a low amplitude. Really, really loud is a high amplitude. And I hope I didn't annoy you with that too much. So let's see if you really just understood what I was just talking about. If an astronaut snaps a tree branch in outer space, does anyone hear it snap? If you said no, you're right. Specifically because outer space is a vacuum. There's no air molecules, so we can't have a pulsating mechanical longitudinal wave that is a sound wave. Therefore, if somebody snaps a tree branch in outer space, nobody hears it. Next, read this problem. Try to figure out the answer. Pause the video. Play it again when you've got the answer. Did you say answer choice number 4? If so, you're correct. Remember, high frequency means high pitch, low amplitude means quiet. Now we're going to talk about something called standing waves. Standing waves are how all instruments, including somebody who's singing, works. Basically, a standing wave is a wave that looks like that top diagram you see on your screen. It's a wave that's been reflected back on itself in a very specific length of an object. So the length of your vocal tract, for example. This is what causes the oscillation that causes the air to vibrate in pulses that allows pressure waves, sound waves, to reach our ears. We're going to do a lot of calculations now, talking about standing waves and the properties of standing waves and how they're formed. And at the end, we are going to talk specifically about how guitar strings are used to actually produce a sound wave that you can audibly hear. However, remember that it's not just guitar strings that rely on the principle of standing waves. It's also flutes, it's also your vocal cords, it's also any other instrument that you can possibly think of. So, logistically, what is a standing wave? Well, a standing wave is a mechanical wave that has bounced off of something and is now being reflected back on itself. The reflection of the original waveform now interferes with the original wave, and it will create this pattern that's actually oscillating back and forth in place. This is really hard to kind of imagine without seeing it, so I definitely encourage you to look at the animations that I'm going to put on this website. Go to physicsclassroom.com, click on physics tutorials, and go to the section on waves. That's actually where I get all your readings from. There's some great animations there, or you can just Google standing wave and look up some YouTube videos, and you can see this oscillation in place. That's really what a standing wave is. Now there's two important properties of standing waves, nodes and antinodes. Antinodes are the part on the wave where it just looks like it never moves from rest position. Antinodes, on the other hand, are the part of the wave that actually oscillates back and forth between the crest and the trough of the wave. Now this is really important because our nodes on the anti-wave need to be at either end of our string or our tube, whatever it is that's actually oscillating. If you don't have two nodes on either end of your tube or your guitar string, then you're not going to have a standing wave, and you're not going to be able to have this thing called resonance and the sound wave that we're going to have at the end. So just remember, important thing, to have two nodes on either end of your standing wave. Now going along with that, we have another property of standing waves called harmonics. Now, since we know that every standing wave must have two nodes on either end, that dictates the wavelength that can create a standing wave in any tube or any string of a given length. So specifically, you can have, if you look at all of these beautiful patterns here, you can see that your first harmonic is a wave that just has two nodes, one on either side. Your second harmonic has three nodes, one on either side and one in the middle, and it divides it up into two segments, it looks like. Third harmonic has four nodes and three segments, and so on and so forth. This actually helps us determine the wavelength of a standing wave. So say that our standing wave is in a string that's 2 meters long. If we're looking at our second harmonic, that's one full wave. So remember, one full wave is like two segments. That means that the wavelength of that wave is just the length of the string, or 2 meters. If you go back to your first harmonic, on the other hand, it's only half of the wavelength, so your wavelength is actually double your length, or 4 meters. We can go throughout this pattern, and if you are in pre-calc and do it in sequences and series, I highly encourage you to actually write out this pattern and try to derive the formula that's shown below. But ultimately, we know that the length of a string for any standing wave is equal to 1/2 times n, which is your harmonic, times the wavelength of the wave at that harmonic. So we're actually going to use the equation that's below that. So the wavelength of each harmonic can be calculated by the length of the string divided by 1/2 times the harmonic that you're currently vibrating at. That was a lot of theory. Let's apply it practically. We have a guitar string, it's 4 meters long. We want to know what the wavelength of that guitar's 6th harmonic is. In other words, you put a lot of energy into that guitar string and it starts oscillating. So what we're going to do is we're first going to draw a picture. So that picture has 7 nodes. So it's the 6th harmonic, n plus 1 nodes is 7. So I can actually then connect the dots, and then I can count how many full waves are in there. The other way is I can just plug it into my formula. So I know my wavelength is equal to the length of my string divided by 1/2 times the harmonic I'm at. and I get 0.75 meters for my wavelength at this particular guitar's 6th harmonic. Okay, I know this is still a little bit confusing. Let's get some more practice. I want you to try this problem on your own. Pause the video now and play it again when you're ready to see the answer. Did you get 1 meter? If you got 1 meter, awesome. Move on, you are ready to go. If you didn't get 1 meter, go back, check your work, and if this is still confusing to you, go rewatch this portion of the video until you really understand what a harmonic is and how to calculate a wavelength for a specific harmonic. So now that we've covered a lot of theory about standing waves and nodes and harmonics, let's talk about how this actually applies to musical instruments. So I already told you that every single musical instrument that I know of operates because of standing waves. Basically what happens is when you have a musical instrument that's a string instrument, for example, that string, which is a certain length, will vibrate. When it vibrates in a standing wave pattern. This can vibrate at usually the first harmonic, which is called the fundamental frequency for that particular instrument. But we can also add energy to that string and have it vibrate at the second harmonic or third harmonic, and having anything beyond that takes a lot of energy and you don't usually see it, but you can create wave machines that can have those strings vibrating at higher harmonics. This is what allows us to actually get different pitches in instruments. So we know that the wavelength of a given harmonic depends on the length of your string or your tube or whatever your object is. And so if you change the length of your tube like you do in a trombone, you can change the pitch that you're playing or hearing. Similarly, you can actually change the material you're using. So you'll notice on a guitar, the thicker guitar strings play lower notes. The reason why is because those waves actually travel slower in those thick strings. They vibrate slower, and thus that decreases the frequency and decreases the pitch. All right, so let's go ahead and check to see if we really understood that. All right, so when you're playing a guitar, all right, you can actually press down on the string farther towards where you are actually strumming the guitar, and that increases the pitch that or the note that you're playing. So why is that the case? If you said it was because decreasing the length of the string also decreases the wavelength and therefore increases the frequency or the pitch of your fundamental frequency or your first harmonic, you are right. If you're still confused about that, go back, rewatch the last slide, check your understanding again. Now we're going to move on to a more complex example that actually allows us to calculate the frequency that's played by a guitar string. This is actually how acoustic engineers design instruments. They determine the fundamental frequency of a specific string or a tube, and they put those strings or tubes together to be able to play notes that musicians can then read off of sheet music and develop melodies. Really, really cool. Anyways, here's the problem. A guitar string with a length of 80 centimeters is plucked. The speed of a wave in the string is 400 meters per second, and I want to know the fundamental frequency of the guitar string. The first thing that I notice about this problem is 80 centimeters. Centa, which I already have memorized as my Greek prefix, is 10 to the negative second, so I convert 80 times 10 to the negative second meters, which is just 0.800 meters. Next, I want to calculate the wavelength. Now the problem says, calculate the fundamental frequency. Why am I not calculating frequency? Well, because in order to calculate frequency when I have speed, I need to know my wavelength first. So I can use the length of that guitar string, knowing that the fundamental frequency is my first harmonic, to determine the wavelength, which is just 1.6 meters. After that, I'll use my wave equation to finally determine the frequency of that guitar string. So I know that a note at 250 hertz is the lowest note that that particular guitar string can play. Now I'd like you to try one on your own. Read the problem, solve it, pause the video, and play the video again when you are ready to see the answer. Did you get 0.51 meters? If so, you are absolutely correct. If not, go back, check your work, and if you need to, go back and replay this video. The last thing I'm going to talk about today is a property called resonance. Now, resonance is when you have one object vibrating at a harmonic, and that causes another object to vibrate at one of its natural frequencies or one of its harmonics. Now, this is actually how all instruments generate sound waves. So a guitar string, yeah, that's vibrating, but we can't hear a guitar string vibrating. We hear the longitudinal wave of pressure in air. So what happens is when a guitar string is vibrating, it causes the air surrounding that string to vibrate as well. That vibration creates a pressure pulse in the air. That pressure pulse reaches our ears, and our eardrums actually vibrate back and forth, creating an electrical signal that goes to our brain, and that's what we perceive as sound. Pretty awesome? Very awesome. Very, very, very awesome. And resonance doesn't just happen with sound and with music. Resonance also happens, if you'll notice, if you take a tuning fork, if you bang on a tuning fork, that tuning fork will vibrate. And if you bring that tuning fork near water, you'll see ripples in the water. And that's another example of resonance as well. And that's actually an example that we will see in class on Monday. I understand that this was a lot of material to take in. I highly encourage you to check out additional resources. So again, check out animations on physicsclassroom.com. You can also Google sound pressure and look at YouTube videos. And I'm also going to be posting stuff on the course website throughout the day later tonight and tomorrow, which is Sunday. Again, apologies on getting this video up so late, but thank you for your patience, and I will see you on Monday.